a significance, but this significance was due to between subject variance, also due to the pre versus post, which is the training, and also due to the interaction of between subject and the training. So this was not quite clear whether training has a larger effect or because the subjects were different. So that is what is making the results to be significant.
Yeah, and again, just keep in mind that we're running this analysis on the using this first HHE transform on the IMF1. So the first transform is being used here. And here is, I guess, just an example of the power from different subjects, right? Actually, let's kind of skip this for a second and talk about this one. So same analysis, right, Pratima? The difference is just we are taking covariance as a subject, right?
Yeah. So here in this analysis, what we are trying to do is take away the between subject variance and use it as a covariate. So we are trying to adjust for the difference that are coming from the subjects. And now we want to see the difference out of the training, which is our independent variable in this case is the exposure pre versus post, and our dependent variable is again the power. So this is good that after adjusting the variances between the subjects, we found a significant difference between the pre and the post. So that is again a good sign.
Okay, and I think this is, I think I found it really interesting here. So if you grab these, right, pre and post, and you look at this, with the subject as a covariate, you can see, the left and right, and this is kind of interesting. What actually the graphs generated by Bill also show that there's this kind of a flip, as you can see the crossover, that the left pre to post is significantly going down, while the right actually has this reverse effect, which pre to post, it's going up. So Bill had those graphs when he did kind of L minus R on his, meaning he was taking at each IMF and subtracting, and the graph virtually flipped its shape from being kind of concave to convex. And I think this also shows the same phenomena in terms of left and right. So again, we're seeing some left versus right, both significant, but each kind of going in a different direction, right, in terms of average power. So I'm going to stop here for a second because that was a lot, but you can see that kind of in general, I think this graph maybe tells us some story that there are differences and they are significant, but again this is using a specific methodology to arrive at this answer. Is this a proper and appropriate methodology to use? Well, we got to maybe do some data cleanup. Maybe we have to normalize the data before we do this. But in a kind of a big picture, my opinion is that, at the end of the day, we probably will arrive at very similar conclusion about the significant results, if we use one of these approaches to data analysis, okay, at the big picture. So let me stop here for a second and maybe let everyone, hear some thoughts and what do you guys think about this?
Yeah, it's an excellent analysis. It seems very in depth. Yeah, I'm not very statistically savvy myself, but I'm impressed. It looks like you've done a much more in-depth analysis than I was able to.
Well, so I mean, I guess we all of us, so with respect to the training, that was performed and the baseline game, I think the overarching question is that we see the same big effect here, that the left side of the brain is doing something very specific here and has a significant change. Again, we can look different analyses. Hopefully each analysis, if it's a wavelet or other transforms we're going to use, hopefully they're going to arrive in the same place. We'll have to check that. But if that's the case, I guess, my kind of a big question is, why is that? Why are we seeing this effect in the left versus right part of the brain? And I don't know if anyone maybe has a guess, I mean, we don't have to be right today, just kind of brainstorming.
Yeah. The IMF1 generally ranges between around 35 to about 50 hertz. And so that would be encompassing the gamma bands. I'm curious, Stephen, what kinds of thoughts might you have on what that could mean?
I'm not really an expert on EEG, sort of what the different, the sides of the brain and that sort of thing. One thing I would say is that what I heard was there was a slight difference in the right and the left in terms of the protocol, and that I can imagine a reviewer getting cranky about that. So we'll have to figure out a way to address that in the publication. That might be worth focusing on.
Yeah, I agree.
In my my understanding that all those wonderful analyses you did, those are sort of different ways of approaching an analysis of the same data. Is that correct? More or less.
Yes, we can. Yeah, this is just an example. I mean, we can go through different kinds. We can normalize the data. Again, there's a lot that can be done. It's just looking for some big patterns. And again, I'm going to open that file, because we could do the same analysis and run and do it for each IMF, right? I mean, we could go from 1 to 8. Mm-hmm. But so far as we've been kind of playing with the data, I think we're going to see statistical significance.
Right.
It doesn't matter which, we're probably going to stick to and see this for the first 2 IMFs, probably most likely, and then perhaps we'll go find something in that 1.6 hertz kind of below. So this is what Bill did. It seems reflects through other analyses as well. So it's kind of replicating itself from whatever angle we look at it. So
right.
We can do wavelet maybe and see if we do a wavelet transform, whatever the Morlet or whatever the wavelet will be, are we going to be seeing similar results?
Right. Well, just looking at the numbers that you have there, I see like there's 48.6 and there's 22.7. That's more than a factor of 2. And mostly wavelet transforms are dyadic. You have each band is twice the size of the one before it. So just looking at those first 2 numbers, those would come out in different wavelet bands. Yeah. So I think here's where we see how the HHT would have an advantage. This is not to say that it's impossible, but there would have to be some bookkeeping, keeping track of which signals were in which bands. So that could be a little bit challenging. Have you thought about a multiple ANOVA, a MANOVA?
Yeah, we've thought about it too here, and we could run it as a MANOVA as well. Yeah.
I mean, if you want to be a statistical purist, if you have a whole bunch of things that you're testing at once, that's what you want to do. But I mean, looking at these p-values, however, the first 2 look impressive. There's one here that's IA6 and maybe IA8 look good, but the others are nowhere near statistical significance. So if you did, if you did a MANOVA, it might actually come out not significant because the 1 and the 2 might get sort of diluted by all the other ones.
Yeah. I mean, of course, this is kind of looking at the t-test is limited in this sense. That's why we kind of this first analysis maybe gives us a hint where, and then trying to kind of go in for more kind of a robust statistical analysis that we were performing. No, I agree. We can run the MANOVA as well in this case and see what happens.
Hi, it's Alana. I'll need to go in a minute, so I thought maybe I should just jump in for a second.
Yes, please.
So the reason I haven't been very vocal about the laterality effect and the IMF interpretation is, for me, that's both of those things are like 2 steps removed from like my area of expertise. So, and then on top of that, they interact with each other. So I don't know the best way to go about interpreting those results. So I guess I have 3 questions. How important is it? How crucial is the effects of laterality? How crucial is it to use the IMF? And could it be a really good starting point, because I don't think a lot of people have done work on this, to start with something that's a more typical type of neural synchrony analysis for EEG and then scale up from there rather than the opposite?
Yeah,
Is there any thoughts on that?
No, I think that also makes sense. I kind of, after doing this, looking through some literature, we are not an expert on EEG or EEG analysis here. However, that sounds like a very reasonable approach for me as well. To maybe start simpler and look for, kind of more robust way of, of not arguing with all the reviewers, right? Also thinking here about the publication a little bit, about what would be kind of a simple way to generate a fairly robust answer for us to see if objectively the EEG data tells us similar story to what subjectively our subjects are telling us. Right?
Yeah,
I mean, to some degree, I'm just trying to get a sense that can we find objectively that these subjects were, I don't know what to say, more efficient, and really in the post-game they were able to do this because they received the training. They were able to relax and focus and be kind of more efficient. The brains were more efficient in that sense.
Yeah, I think that is worth looking at in and of itself. And then, because like I was telling you earlier, I haven't seen any literature on the IMF. I went looking; it was sort of harder to find. There's a lot of great work that's been done on phase amplitude coupling, within EEG signals. There are a lot of people that are producing clean data, but never applied in this situation. So I think I don't know that we need to create the wheel in this sense, unless there's something that we see that's flawed in the work that they're doing. But so far, as I can tell, I think they've done a very good job, and it's worth implementing what they've done and following their example.
Yeah, no, I think, I mean, I don't mind looking at the, basic and then, and starting, as you mentioned, simpler and seeing what that results are, and then be able to agree as a team, as we work on it, which analysis should go into the publication, which we are, I would like to say we are trying to publish maybe a first paper in a kind of a healthcare informatics, which, reviewers are not neurofeedback or EEG experts. They will be looking at it as a, as a study where we are talking about can neurofeedback has potential, to help physicians in general, offset maybe some of their, work-related stress and learn, how to, be more kind of, be more attentive and focused and more relaxed during the work hours, where they're actually interacting with computers, because here also we are thinking about this human-computer interaction type of a stuff. So it's kind of a high-level paper, not so much more methodological yet. Maybe this data can serve the basis for something more methodological, comparing and kind of doing a little bit more EEG neuroscience type of a study, but maybe that's a second level of analysis and paper we could generate in the future. What are the thoughts on that?
Everybody, I have to apologize, but Deborah and I, we have to excuse ourselves. We have clients to see. So thank you very much for the insightful talk. But we have to go, unfortunately.
Bye, David, and we'll talk with you next time, Deborah.
Okay, thank you.
Goodbye.
Bye-bye.
Yeah. Yeah, I think going for a more traditional measure, given that there's a lot of work already done with amplitude coupling and phase amplitude coupling, that makes a lot of sense to look toward them. In your toolbox, Alana, that statistical toolbox you were mentioning, do you have something that you can do amplitude and phase amplitude coupling with? Do you know? Or
phase amplitude, yes. I'm not positive that someone's written a specific script to do amplitude.
Amplitude coupling, that's saying that if the power in one band goes up, a power in another one goes up as well?
Yeah.
Or there's a relationship with them, yes. It wouldn't necessarily have to be a direct relationship that two go up at the same time. It could be that one goes up and the other goes down, for example. But looking at the amplitude, yes.
So that sounds like a correlation.
It is. It's just corrected for the time series.
Right.
Yes, exactly. David Kaiser, one of the authors on my previous, on the 2005 addiction study, had actually was one of the sort of pioneers in that methodology. But
although,
yeah,
I think AxMatcher actually uses amplitude with just a correlational correction for some of the covariance. It just took a few steps.
The limited file.
Yeah.
Okay,
Yeah.
interesting.
But maybe we can set up another email chain and send some things around. I do have to run, but I'm happy to talk with people more about what maybe the right wavelet choices are, or if we want to look at what others have done in the past that might be the most robust analysis.
Yeah, I would say maybe we could try this, through the being on the email chain, and maybe what we could share is, the approach. Everyone could maybe kind of chime in and says what approach, that they believe is the most appropriate to use, so we can have a short discussion through email. And then if we agree on the, maybe one or two or three of these analyses, maybe we can then, the person that proposes can actually run the analysis and maybe share, using Word document, some results, or PowerPoint. And then, if we feel comfortable, maybe we come together on another call and we kind of hash it out and then say this is what we would like to publish.
Excellent. That sounds excellent. Great idea.
Sounds good.
Well, Anna, yeah.
Thank you. Well, it was nice to chat with anyone, and we'll continue conversations over email.
All right.
Thank
sounds
you.
good.
Bye.
So Bill and Steve, I don't know if this is this is just to give you guys a sense. I'll send these PowerPoint just for maybe a record and looking over. But as you look at my screen now, I mean, we did some, not necessarily this is 100% accurate, but we did on the raw data files. I kind of extracted these bands and ran pre and post kind of T3, T4 pre, and then T3, T4 post correlation analyses. So we did some of that. So as you can see, the correlations itself kind of post, they kind of drop down a little bit. And then the slides that I'm going to send to you guys, they also going to have a little bit of a coherence analysis, which again is on the raw data file. So there's some noise here that has to be probably taken out to the degree. But I just wanted to see what it is, just quickly running through those. The interesting thing, I'm not sure if this is because of the subject or there's some problem with with the raw data file that has to be removed. But if you look at where we found the significance in the IMFs, this is kind of a raw delta pre and post, and you're looking at the coherence from estimate from 0 to 1, normalized frequency in that band. So you can see kind of where that coherence estimate kind of goes up. So the one interesting thing, I'm not sure if this is something because of the noise in the data that has to be removed, but you will see these spikes on the edges, which also shows maybe that there's a problem with data itself or approach. But let me flip through this. So this is delta. You got theta, alpha virtually flat, nothing there. Then you look at the beta. Again, there's this kind of an increase in coherence, on this end, and then you have to see the same thing in the gamma band. So I thought, at least I'll throw it out there and see what people think in terms of doing some of the, and I would say more sophisticated in terms of trying to look for coherence and phase amplitude analyses here. So I'll send this all off. Not to be maybe discussed and spend too much time on it,
Okay.
But I appreciate you guys, your thoughts on it, and I'm very excited about this work. And again, I hope maybe in the next, I don't know, few weeks, 3-4 weeks, I'd love to, as a team, decide on the appropriate analyses, and then I'm more than happy to write the first version of the paper and then send it to everyone, for review and kind of making sure that we all like it, what's going to be published, and keep it maybe a little high level first. Go to the informatics kind of medical journal, and then maybe in the future, if we have some interesting findings, maybe attack a journal where reviewers are definitely more rigorous and probably would require a little bit more sophistication in terms of methods. I don't think that medical informatics type of a journal will be really that aggressive in terms of reviewing the actual methods. I think they will go on to some degree on a little bit more trust here of the expertise of the authors.
Okay, can I ask a couple questions?
Yes.
Okay, so what we're looking at right now, the coherence. This
Yes.
is right-left coherence?
Yes, so this is exactly. So I took a pre-row, I extracted the gamma band, and then I look at the left-right coherence for pre, and then at the bottom graph you see the same approach but for the post data.
Right, so it looks at, yeah, those big bumps right at the edge. I mean, you're right up at the Nyquist limit there.
Yeah.
So that is sort of. I would wonder what that is. So it looks like what that's saying is that right at the Nyquist limit, the right and the left hemispheres are completely opposite. They're. Am I understanding that correctly?
I know. Yeah, I'm not. I don't know if I can answer that question. That's where I'm kind of a little weary on exactly interpreting the result here.
Okay.
So the amplifier, it samples at 256 samples per second. I'm curious, how are you gaining? Where are you seeing sample information, Stephen, with that?
So this is, kind of the approach. So I have a slide here just to show you the function in MATLAB that I used. And again, guys, just to be honest with you, first time I've used this function in MATLAB. Never ran the coherence analysis in my life before on EEG data. So take it with a grain of salt here. But I used a window of 256, and I used the overlap of half of that window of 126. So. So we overlap that with, we took, if its sampling rate is at 256, I overlap that window with 128, and I ran this function that, tries to look for that coherence in this case. So.
And what window did you use?
256.
That's NFFT, right? 256. I'm just looking at the third argument there, the window. Is that the shape of the window?
Yeah. So that it's. Let me actually. I'm gonna pull it up for you here. I think I still have it. So instead of.
No, as long as it's not a rectangular window, it should be fine.
Yeah. Where is that thing? This one. This one. This one. There we are, guys. So this is you can see that this is the function and explanation to the parameters.
Mm-hmm.
In that function that I use in MATLAB.
Mm-hmm.
So it's interesting. Just when I was looking through all those results, and we were from different angles. We still see kind of this overarching, maybe a conclusion here that something is going on at these kind of high frequencies, right? Gamma, high beta. There's something going on over there, and maybe there's something going on with that, it's not a high signal, but maybe with the low kind of, delta 1.6 hertz. So it seems like at least there's a little bit more coherence when we talk about these high frequency bands right there.
Mm-hmm.
What does this, seems like you've had some experience, Stephen, so what does this tell you? Like, how do you interpret when you see this result? What do you make of this?
Well, like I said, I'm not. Most of my background is not EEG, but when I see something that looks, I just. What you've done is great. I don't. This is you said this is sort of a first pass. So I don't want to cast any stones here, but it looks like the lower plot here. It goes all the way up to 1, which is the highest it can possibly go, and the shape looks sort of like a window function.
Yeah.
So that I just want to make sure, in terms of if this is going to be in our analysis somewhere, that we're sure that this isn't some sort of an artifact or something.
Yeah. My first impression was looking through that. This looked to me like on this site was an artifact. So, that was my first impression, that there's something in the data and procedure that causes this, to go that nicely, from to 1, right?
And the frequency here. Normalized. So this is normalized frequency. Is that x-axis we were just looking at?
Yeah. So you're looking at 0 being 36 hertz and 1 being 44 hertz.
Okay.
So for that gamma right there, that's really normalized, really going to 44 hertz versus 33, whatever that was. That's being known because it's run across all the subjects. So this is not one subject. It's run across. I keep the time when you do the extraction of gamma band. I keep the time. For all the subjects, the time is virtually kept. So if there's no gamma band in samples of 1,000 to 2,000, and that we take that into account virtually. When we process the data.
Mm-hmm.
I thought that was kind of important to kind of have this, time variable kind of done. So it didn't, that procedure here, if you look at alpha, we don't get that effect of the window, right?
Right.
And then, but we definitely have that effect in delta. We can see that in theta. Then alpha, that shows virtually flat. I kind of get the scale. I blew up the scale. So if you blew up the scale, you can see this close to 0.5. There's a little bump there.
Yep.
Right. So of course I kept the scale of y-axis constant throughout this slide. So I kept it from 0 to 1. But if you blow it up, there's definitely, if the effect is very small, this line doesn't look flat. I mean, definitely there's a lot of ripples, but we are talking below 0.01, right?
Right.
Very tiny kind of effects. There's another effect in post only, not in the pre. And then
one thing too, Stephen, with this is it's the same. If you're wondering if it was like some problem with the amplifier or something like that, it's the same exact amplifier that was used in both the pre and the post, also, just for what it's worth. Mm-hmm. Same computer and amplifier. But, were you thinking that there might have been like some kind of a problem, like with the hardware or something like that?
I was wondering. Yeah, I mean, if you had, just off the top of my head, if you had like the last bit of the A to D converter or something was alternating back and forth or something, for some reason, so there was some very fast, something like that, that might show up. But that's when I thought that the 1 corresponded to 128 hertz, but evidently it doesn't.
Right. Another thing too is that the samples, they did them in relatively similar time frames, but some of them had finished much earlier than others, but it wasn't like they'd all finished on the same day either. There were some who had started pretty close to around the time that others had been finishing. But again, it's only, I think, 6 or 7 subjects in the entire sample, though, too. But
mm-hmm. If it were me, sorry, go ahead.
No, go ahead.
If it were me, I mean, I don't have MATLAB, but I would start playing around with that, like that raw beta post. I would look at like the subjects and see if they all have it, and then I would look at, if I could chop it up into small pieces, does it show up all the time, and try to sort of nail down what is it about the data that generates that big bump right at the edge.
Yeah.
And then that way I would, and I may be able to help with this, it might actually be worth running a different sort of, not using MATLAB, maybe doing this in a completely different way and seeing if I get the same results. But I would want to understand that to make sure that I trusted it.
Yeah,
but from what I'm hearing from you is that, sort of take the larger picture, maybe it's not worth spending a whole lot of time fussing over this if the main point of, depending on the main point of the paper. If in terms of what sort of data to present or even to analyze, I think one question is, what is the point of the paper? And if you're making a high-level statement about the efficacy of this method, this treatment, then maybe just focusing on those self-report numbers is the most important thing.
So that's what, that's where I'm kind of looking at maybe analysis as, like, Pratima was showing on some kind of more formal, because maybe the first message as this training, this objective, I would like to definitely report in the paper, the method's going to have a subjective section, right? Subjectively we've collected the data, then objectively we have collected the data, right? So there will be a kind of two approaches here to confirm, this intervention. So we say subjectively we can see that there's significant difference, and then objectively, now we'd like to nail it down to an analysis of the EEG signal, to also to say that we feel comfortable as a team, and say, and that also shows that this intervention was successful in this sense. So looking just as a graph like this, right, we can approach this maybe differently, but it seems to me that hopefully whatever analysis we use at this level, that we'll see that as we're going to be looking at the left side of the brain, you're going to see significant effect, hopefully, in terms of and going, on the slope this way versus, you're going at the right side, which is kind of reverse. So I guess, my big question is, why is that? And again, is this what would be expected if we would repeat this study with another 7 physicians? Kind of, can we replicate this? And this is really what should have happened, and that's why they felt what they felt.
Mm-hmm. Yes, I think that would be probably a real valuable thing too would be to show, well, is there a consistent finding that is replicable in the EEG? Might be the next. But here's our methodology. Here's how we trained. These are the analysis tools we use pre and post. Or can we replicate these? Because one thing we know, if we were to just look at the FFT-based values of the amplitudes, in the vast majority of studies that show when you're rewarding beta, for example, more so than beta, SMR, that some of the beta studies, you'll see people physically tensing up, and you see their faster frequencies increasing disproportionately than their actual 15 to 18 hertz beta will increase, only when they're physically tensing up or when they have more of this high beta increasing. But when it comes to rewarding this, what's most frequently called low beta, or we call SMR, that the vast majority of studies in humans have not seen the FFT-based amplitudes of that increasing. So the majority of studies, when we're just looking at the FFT-based filters, pre versus post, they're not showing real consistent results. And that's one thing that's really lacking in our field, is that ability to look at, is there just, yeah, it would be great to figure out what these EEG changes mean at some point, and what they might mean in terms of brain function. But one, is there just a consistent change that we're seeing among studies? Because when it comes to, it seems that when you're using linear measures for nonlinear data, and then you do a post hoc analysis, you'll always find something statistically significant in it. It just won't be real consistent from study to study. And one of the things that I like about some of these more nonlinear adaptive filtering technologies is I suspect they have a much greater likelihood of yielding some consistent effects in the EEG pre and post. And then maybe when we start doing some fMRI studies in addition to the neurofeedback pre and post, we might be able to then generalize some of the training effects in the EEG to actual brain function. But the why questions are very difficult to answer, but the what happens, or what are you likely to find if you replicate this work?
Yes, I mean, the HHT is a nonlinear data-driven sort of analysis, and I was just sort of noticing the p-values that we were getting, and sort of the more conventional analyses, they were certainly respectable, but not dramatic. And some of those F-scores, there's some with like, one of those have like 5 or 6 digits or something. There we go, 5 digits. I mean, that's incredible. So I mean, that's what that tells me 2 things. One is that the HHT is sort of zeroing in on something that's probably truly important. And the other thing is, like a p-value of, I mean, what is that now? Is that 23? If you could go back to that one slide where you had that huge F value.
Right here?
There's one that was like 23,000, I think.
There was one that was 23,000, yeah. No. It was the same format as that, but it had 20. There it is, 15. Yeah, 23214. And that's 6 degrees of freedom for both?
Yeah.
Okay. So I get 2 times 10 to the minus 12 for the p-value. So I mean, I would say the odds that if you did another 7 physicians and you repeated the experiment, I'd say the odds are pretty good that you'd find something.
Yeah.
So in other words, it's the odds that this is a fluke, if you believe those numbers and the validity of the ANOVA, the odds that this is a fluke are less than 2 in a trillion.
Wow.
So.
Right. I would say that's clinically meaningful.
Yes.
Yeah, and and this is that interesting one, like right here. So this is run on the on that first HHT transform, right?
Yep.
It's taking the IMF1, and it's really kind of trying to adjust, in this case, for subjects, right? So we put covariate as subjects. So really we say, okay, we're going to take that into account, right? So really what is being the independent variable, it's just the exposure here, pre and post. So I think, that's kind of a, taking into account that we say that subjects are not, and we could do this, repeat this analysis on normalized, right? We can just force, we normalize the values, which would maybe, change the result a little bit, but I don't think it would change the result, dramatically, so to speak.
It's not going to go from 2 in a trillion to 0.06.
That's right. That's right.
Yeah. I guess I would like to see. Those are the same, and this is the same numbers that you were showing in that spreadsheet.
Are they, Lucas, or are these from the full unartifacted files? There are 2 sets of files. There's some that are like 2 megabytes each, and then there are others that are like around 90 megabytes each.
Yeah. So I mean, so this is taking the raw data, the whole file, which is the big file. There might be.
Oh wow. Okay. Yeah.
So, but there's a problem of to some degree we would have to look through and remove the I have a picture of the raw data, so I wanted to show you guys. So you see, if you look at the raw data file here, this is in this other software that I'm using, the Acknowledge. So you can kind of look at the whole. So you can see that I kind of put all the subjects together. So you're looking from left to right. Subject 1, 2, 3, 4, 5, 6, 7, kind of all put together. So you can see that there is a bump in the middle. Well, that's one subject. That's someone else. I'm just kind of displaying this here, to show you that there are, 7 subjects worth of data, and you can see raw data pre-left, raw data pre-right, and then, as you go down, the blue and the green are post data left and right. you know, there's still some artifacts right there. You can see all these kind of, right? Easily to see that all those spikes that are over 70 volts and stuff like that, I mean, that has not been removed in that analysis yet, and should be removed. You know. But again, would that change the overall conclusion? I don't think so. Yeah, the p-value will change, the f-value will change, but I was just kind of running at the level because we started to do these analyses on kind of always short on time doing a lot of projects. So, you know, I was just trying to kind of get something for discussion for today, right?
Right, this is great.
Yeah.
So there are some of those, you know, some of those things here.
Can we go back to the last slide with the 20? There we go. Now, all right. So when you ran this ANOVA, you have looks like this is based on just 14 numbers, right? The ANOVA.
Yes.
Or 28, I guess. Left and right, pre and post for 7 subjects. Or
Yes,
no,
so
two sets of 14. Sorry, one for the left, one for the right.
That's right. So you have 7 subjects, and you have left and right, yeah.
Okay. So are those on a kind of a mini spreadsheet that you showed earlier?
No. So that spreadsheet was generated by Bill. You know, which this spreadsheet? I think you're talking about this spreadsheet.
Oh, okay. Okay.
So this is, you know, this here. What you're looking at is the percent power, and the analysis of the t-test. You are taking the, you know, kind of for each instantaneous amplitude, you are calculating the percent power, which is really your amplitude divided by, you know, sum of the amplitude across the IMFs.
Right.
Right. So this tells you that there's 22%, so it's all equal to 100, and then you find the median of that. Right. Well, the t-test really runs, as you can see in the formula, is these numbers as a sample versus the post, which are this right here.
Okay.
Right. So that's the t-test, which again, you know, is just a quick and dirty way of just getting. I think
right.
we built it nice. Just kind of take a look at it quickly and say there are potentials here for analyses.
Okay. Can you, for the page of the 23,000, can you send me those 28 numbers?
Oh yeah, we can send you guys the big spreadsheet. So we're probably going to have to post it to the we'll post it to that share drive.
Okay.
Because, you know, we're talking about the Excel file that has like 500 megabytes.
500 megabyte Excel?
Yeah,
I
actually ran out of space in Excel. Believe it or not, I can tell you that Excel has, you know, what's the length of rows in Excel? Because when I was constructing powerful analyses, Excel virtually stops at you know, 1,400,000. I don't remember the number, but it stops at certain row and doesn't let you kind of add data anymore. So Excel was not the best way. So then, you know, we kind of constructed the files in MATLAB and SPSS, which kind of allows you, you know, to use more rows for analysis.
Can you just send me the not the 500 megabytes? Can you send me just the 28 numbers?
Yeah, I can. You know, Pratima just left, so she's got that spreadsheet somewhere on her computer because she ran that ANOVA. So I don't have it on my computer, right?
It doesn't have not necessarily today, you know, but at some point. Because,
we'll send it to you.
Because one thing I want to be careful about, the ANOVA is a classical measure, and it assumes that your data is normally distributed.
Yeah, that's going to be a problem here, and I got to tell you that we have to normalize the data because, you know, the data usually is not probably normally. We ran a normality test and we ran the test, and they are not being satisfied. So one thing that to keep in mind, you know, that's we will have to normalize the data and rerun this analysis.
Right. So there's a number of ways to go. One is to, you know, if you know, for example, from the physiology or the mathematics or something that it's not, if it's, you know, it's not a normal distribution, but it's some other distribution, you know what it is, and you can transform it so that it becomes normal.
Yeah.
The classic, if you have log normal data, for example, you take the logarithm and then it's normal. It solves that problem. If not, then you use a non-parametric test. So that's what I was just thinking. You know, if I could, I'd like to look at the data and see, you know, is one of the numbers, in other words, is one of the numbers a whole lot different from the others? That would tell me something.
Yeah. So yeah, you can see here that there is one guy.
Oh, this is the data?
This is you know, this is some of the data that we just put there. You have, as you can see, pre and post 7 lines, right?
Uh-huh.
IMF power. So here's to some degree kind of a look at the data, right?
Mm-hmm.
Of the average, you know, of the average powers here, you know, that you are. You know, we're running ANOVA on all data points, so you're looking here at their average numbers, but so this kind of gives you a sense of like one subject number 4, definitely seems, you know, that his numbers are a little high, right?
Well, yeah, but that's not unreasonable. He's not totally out of whack. I'm talking about, you know, the numbers like 1, 3, 6, 12, 4, 9, and 3 million.
Yes.
Something like that. You know, that would give you an amazing ANOVA answer, but then you wouldn't trust it. All right, so yes.
Now I'll send you the files, and we got to look into this, you know, as well. You know, I didn't actually right before Pratima sent me the files, I didn't even spot this large F value, to be honest. Now as you pointed to it, you know, I'm like, oh yeah, this is a pretty large F value. I didn't even see that as we were kind of, you know, I look at the p-value all less, you know, kind of glancing through it. But you're right, we got to kind of take a careful look at these large F values, and again.
And I'm sorry, I don't mean to criticize you put this thing together and I didn't, you know. So I mean, good. This is a wonderful start. I just I've been burned by these sorts of things before. I just thought I'd mention it since I saw it.
No, that's perfect. That's why we, I guess, doing this, and at the end, you know, not make some silly mistake. You know, but, you know, again, you know, we will clean up, we'll look a little deeper, and we'll share the files and everything with you guys. And I guess, you know, we'll see if the whole big picture changes. But kind of perhaps, you know, what we will continue to see is what Bill sees in his analysis, you know, going back here, what potentially we see in our analysis, because the same pattern kind of evolves, you know, and then as Bill kind of pointed here when he's doing this, I think I have it actually on the slide. As you can see, this flipping left minus right, where is it? Actually, let me open my slide that caught my attention all the way to the top. As you can see here, the symmetry, which, you know, is kind of taking L minus R from pre, and if I flip to this time slide, and kind of, as you can see, the post, right?
Mm-hmm. Yep.
Right. I mean, that same effect that one side of the brain is doing one thing and the other side is kind of going in the opposite direction, right?
Mm-hmm.
At least the bump. So I think both analyses are showing very similar pattern. So I'm wondering if other analysis will kind of get maybe, you know, different numbers but same pattern and same kind of an overarching conclusion.
Looking just at these two things,
one potential artifact that could be happening with this particular data, with these graphs with the left versus right, could be that this is from the artifacted data that was taken from 1-minute samples. So there could be some where the left data isn't going to be synced with the data on the right from each. This is just sort of an average. After the data, whenever there's a how the artifacting algorithm is, in this data that we're looking at that created these graphs, came from if the raw signal was over 45 microvolts, it then rejected that segment out of that hemisphere's data. So it didn't reject both hemispheres simultaneously, which, just looking at the amplitude, shouldn't matter if we're looking at like at a minute of data. So we have a minute of the data on the right and a minute of the data on the left. That shouldn't make much of a difference, because the artifact should be pretty equal. If somebody moves, both sensors are likely to move equally. But other level, when it comes to the phase relationships or the amplitude coupling that we're looking at, that I don't see that we could use these smaller files given the nature of that artifacting that I used in that algorithm. Then we would need to use those 100 megabyte files that you graphed out the raw on the left and the right to do that analysis. But Stephen, could that, the way that I had artifacted that data, do you see how that might create an artifact in these statistical analyses?
But again, you guys,
the process of starting with the raw data and then doing the artifact removal and then all the subsequent processing and ending up with plots, it's a series of linear, nonlinear steps, and I can't really sort of tell you off the top of my head, but it wouldn't make something appear that wasn't there, or vice versa, but I suppose it could make one of the numbers quite different, sort of. So I suppose it's possible. In other words, it could fool a conventional analysis. I don't think it could fool a non-parametric analysis.
Oh, interesting.
If that makes sense. But that's just a wild guess on my part.
so like as you, and when you look at this file right here on the screen, I mean, looking at the raw data here, any big concern right away jumping, just looking at the raw data across all the subjects?
I'm not the expert here, so.
I wouldn't say so. I mean, it's, one thing is, if I understand, this is like all of looking at that dark blue line you're pointing at now, that's left hemisphere pre-study of every subject from start to finish, all of their brain waves, or
So you
all
just
overlap, kind of added together, is it, or
no, just
together,
like
or?
stuck together. So like, up somewhere to here, there's a subject 1, subject 2, this is subject 3, subject 4, subject 5.
Okay, I got you. Yeah, I follow you.
So you can see that this guy is
overall, I wouldn't say that there's too much. What it essentially is some of, like the one, point over to the next burst to your right there in that dark blue, the next kind of larger signals over here in the, or to your right, yeah, there. That is probably someone with some large eye blink artifact, given that they're getting high. But there's fewer of those larger artifacts than there are smaller ones. So that's not going to completely contaminate that data set. So no, I don't see anything glaring in that.
Yeah, that's what I was kind of thinking, like even looking at that, why we have these, in ANOVA, why we're getting this. I mean, you see, this is all the data, so there's nothing here that would cause, a point that is 3 million versus, something smaller, right?
No, I'm not seeing anything.
I couldn't find anything that made me kind of concerned when I look at the big picture of this data and saying, okay, I'm just going to run it using all, because I wanted to kind of preserve the time fashion, when we were doing the correlation, to keep the lengths of the same and coherence, to keep everything kind of on the one scale without necessarily, removing anything or interpolating. So I looked at this and I said, well, let me just kind of go ahead and use these files for this first pass and look for patterns, even knowing that, of course, there's still an artifact to be removed. But I couldn't, like really look at it and say something is really bothering me in terms of a lot of artifact that would be completely off.
Right, yeah. I think too, when it does come to removing the artifacts for analysis, we'll just want to make sure that when we take some of the data from the left, that we're also taking it from the right. Or perhaps if we could find a segment of maybe even like 30 to 60 seconds of the most artifacts free from the samples. That's a convention I've seen used before. I think even with fMRIs, they do. Oh, that's totally different. But what are your thoughts on that, Stephen, of finding, so that, because if we were just cutting the data up per a certain artifact criteria, let's say, for example, there's some No, I guess that should all get averaged out, I would think. If you were removing both the left and the right, whenever there's a significant artifact criteria in the left or the right, just that little shift in phase that might happen from one data point to the other, I don't think should throw off the whole analysis of looking at phase relationships, unless we were cutting out, if we were artifacting out every second some piece of data, which clearly wouldn't be the case. So I don't think that should be a problem, artifacting it and still looking for phase relationships, just provided that whenever we cut out something from the left or the right, that we're also taking the equal amount of time from the left or the right.
Yeah, I agree that if you're going to do, if there's an artifact anywhere, you should remove all the data. That seems, I think that's definitely the way to go. And it would be good to have larger chunks. So if you end up with some small pieces that are artifact-free, it may not be worth including them, because every time you have a join between these two things where you've chopped out data, then there's a discontinuity, which adds a random, sort of in the Fourier space, it adds like random phase. So you get this sort of broad bandwidth thing that's sort of added right at those points. So every time you have a discontinuity, you get one of those. So if you have a few segments, then almost all the energy is going to be in the signal itself, not from the discontinuities. But if you have lots of small pieces, then that could be a problem. I mean, in an ideal world, you could take the pieces and analyze them separately, and then average the results of each of the analyses, if that makes sense. So, like in other words, if you're doing a Fourier, like if you're estimating like a spectrum or something, normally what you do is you chop it up into these, like what we were seeing before with that coherence. You have a bunch of short-term Fourier transforms, and each one has its own window, and then you move the window like half its width all the way down the data set. And then you take the results from each of those, take the Fourier transform, and you square it, and then you average it, and then that's how you make that's like one way of estimating the spectrum. So if you have all these little pieces, then what you could do is you could do the same thing, and you could keep moving down the length of it with all these windows, but then basically not allowing the windows to span any of these discontinuities.
Yeah.
Okay.
So hopefully your EEG software is doing just that.
Right.
It's black box, I will have to see what it does really behind the scenes. So I usually try to run the final analysis in MATLAB because it seems like more trusted, than this is also like this acknowledge is kind of a black box, it has
right.
a lot of analysis that I can do. As you can see, I go to the menu, I have everything in the clicking, and there is a little manual that comes with it, right? But exactly what it does, it's maybe something I will have to kind of dig out to see what the software is doing behind the scenes.
Right. The black boxes can be dangerous if you don't know exactly what's going on.
Yeah. So I don't really do, I do a visual inspection of data in Acknowledge.
Mm-hmm.
I play with it, I quickly kind of run some analysis just to kind of get a sense of it. But then if we're doing something for a paper, I try to do everything in MATLAB.
Okay.
So that's kind of my usual approach, that final result. So, for statistical analysis, we would use SPSS and other statistical analysis packages out there
mm-hmm.
that are more trusted, to kind of run the p-value analysis.
Okay.
So that's kind of the approach. Well, so guys, so I think, this was, I think we, what I hope that I sent, of course, the files, but it seems I spoke with Alana here, a few times, and Asha, they have a lot of expertise in EEG analysis. I mean, that's virtually what Alana does. She's a postdoc, and her expertise is strictly EEG processing.
Okay.
So she seems like she really grasped this pretty strongly. So what I kind of agree with her is that, let her come up with the methodology that she would like to offer and run the data through, so she would, so that's what I think she said at the end as well. So I kind of say, why not? We can all, on the email, review it and provide concepts. If Stephen and Bill, if you guys have also, I think, Bill, you already offered it, and I'm still saying if HHT, the way we've done it, maybe with some modification, is still something we want to publish, I'm happy to do so. Again, I don't have that kind of a final call here. I don't think I have the expertise to say which way to go at the end. I keep playing with data myself. I learn as I do, so it's always good learning for me to try to run different types of analyses and learn about EEG. I went to a training a couple of weeks ago with John Anderson. I think he knows you well, Scott.
Yeah.
Bill.
Yes.
Yeah. So I went for the training for 4 days in New York and got a little bit of neurofeedback training and passed a little certification. So I can do some work with healthy professionals here in the lab myself.
Oh, nice.
Connecting. So I found it really interesting. In my opinion, I've done some training myself, and I kind of have a sense of, after hearing responses of the physicians, which were very positive, except the skeptics that you have in your end, they just from the beginning there's something is wrong for them. But overall, I really felt like the physicians said that this could be a way for them to learn how to, kind of relax, maybe train attention, because specifically the physicians in radiation oncology, they spend most of the day in front of computers, right? They do their surgery on the computer. They have to count these tumors, and most of the work is sitting, and it's still a very stressful environment. So the idea is long-term to see if healthy professionals, like healthcare professionals, could be utilizing neurofeedback as a way of training themselves, for specific cognitive state, right? Maybe kind of more relaxed and attentive,
Yeah.
And that's kind of the whole big picture.
That would be great, and perhaps some future replication if we could look for actual data in terms of error reductions. Usually with those kinds of systems, with healthcare systems and insurance companies or whatever, there's some statistics that they tend to keep on error rates or false positives or things like that. It would be great if we had some actual outcome data like that, sort of pre versus post, of how many errors they're making, due to perhaps inattention or fatigue or things like that too.
Yes.
Might be a future.
Yeah, and I agree. So, my goal would be to submit a proposal, to like IHRQ, one of the government, agencies, and ask for like a long-term 2-year study where, neurofeedback would be administered over time, longer period of time. We're talking maybe, 30+ sessions spread out, or maybe, somewhere 30 to 50 sessions over the year, or 6 months, and then look at those results in terms of how the entire clinic functions when we have a unit of people taking neurofeedback, and saying that that's training, the unit, and looking at the performance of safety, efficiencies, things of that nature, satisfaction, work-related stress, and then so I'm trying to do this study first to have like a preliminary, thing that could be submitted to the government. And I really would like to have a methodology that we could stand on, right? Something basic that we can say this preliminary study is a foundation to move forward and do larger studies. That's why I'm kind of trying to pull, Bill, great that you guys, are joining the team. I'm very, very happy, and we can work together to come up with a, approach that we could replicate. And I think for me, it's always kind of that question, when I do research, is that if someone in Washington State or whatever wants to replicate the study, and they do the same intervention with similar subjects, I hope results would fall kind of in the same bucket, and that's what I hope to do, with the methodology.
Right. So one other thing too, for a point of reference, is the number of sessions that they did is actually among the fewest sessions ever done in sort of neurofeedback history, where people have, with 6 sessions like that. There's a couple fMRI studies that have done, pre and post 1 session, but also that if when we're done with our final analysis, maybe perhaps when Stephen gets those 28 numbers and does the MANOVA on the data, if that still is holding up to statistical scrutiny, that will be quite remarkable to show some large effect size with new sessions also.
Yeah.
That would.
And and Stephen, I will look very closely starting tomorrow when Pratima will. Again, this was kind of done. You pointed to, so I'll also look very closely to, and we'll rerun some of these analyses with MANOVAs and things. But I'll send you that. I'll send you the numbers that we ran, and the more then you look at it and see if we all are arriving at similar results. And I actually, I do think that probably running that, removing these artifacts, which actually maybe is jumping at me, that maybe all these eye blinks, that those might be. They're causing maybe some of the coherence of that end of the spectrum, end of the normalization of one, because I would assume maybe, I'm just kind of guessing here, that when someone is blinking both eyes, maybe that's causing left and right part of the brain to generate something very coherent in terms of a response in EEG.
Oh, there is a phenomenon that's, I think, relatively recent that they call attentional blink, that when people blink a lot more than they actually need to lubricate their eyes, and it seems that there's another function for blinking, which is sort of resetting memory and attention. It's possible that after the study, if we, after the 6 sessions, that people change their attentional blink, that could be reflecting less slower. Yeah, but we actually saw the opposite. We saw more of the slower frequencies increasing in amplitude after the study. So that could speak to more of an attentional blink, perhaps.
All right.
Very good. Well,
all right. So I'll share the files, with Stephen. We'll do some analysis, and I'll try to maybe write just a kind of a nice short summary, what has happened email to everyone, and connect us on the email with Alana and everyone that was on the phone call, and then see if people, as they have thoughts, I would hope, and time, of course, people could respond and say, hey, I've done something here, what do you think? And we can maybe start a little bit of an email, kind of a group email conversation on what we're doing.
Oh, nice. Also, if everyone is okay with this, right before Patina left, I started recording the webinar for her. If everyone is okay with it and you'd like, I could put it up as a private YouTube video link for others to see what they had missed. But again, are you two okay with that, or
that's fine?
Not?
Yeah. Okay. I'm definitely fine with that.
All right, and so then I'll email that link to everyone also.
Yeah. So that I think that would be the plan, and I do hope that hopefully maybe in the next few weeks, 3 weeks, we could arrive at some conclusion on which method to use, because I'm excited to get this publication submitted maybe by the end of the summer, and if not sooner, and kind of go from there and thinking about potentially some larger research studies.
That sounds great.
Yeah.